Hello everyone, and welcome to today's chem lesson. Today we're going to spend some time talking about these three properties of gases and how they relate to each other, how changing one will affect another. We're going to look at temperature, volume, and pressure. But before we can look at these pairs of properties, we want to define these things in a way that allows for us to think about these things in terms of gas particles. So for temperature, which we've previously defined as the average kinetic energy of a substance, now we're going to define it as the average kinetic energy specifically of our gas particles. Temperature is going to measure how fast the particles are moving. High temperatures means fast-moving particles. Low temperature means slow-moving particles. Volume, the amount of space that the gas particles take up. This can come in two different ways. It could be the size of the container, right? A bigger container has a larger volume than a smaller container. And because gases take the shape of their container, gases that are spread out have a large volume, and gases that are more confined have a small volume. Lastly, we're looking at pressure. Pressure is a measure of how often the particles of gas hit the walls of their container. So, if I have this box with this gas particle in it, as it moves in its continuous, random, straight line motion, pressure is a count of how often it collides with the walls. Something that collides with the walls frequently has a high pressure. Something that does not collide with the walls frequently has a low pressure. And so through over the years, different scientists have studied different pairs of our properties here, right? Pairing temperature and volume, volume and pressure, pressure and temperature, right? The three pairs that we can make. And they found how influencing one affects the other. But before we can talk about how these properties change, we need to know what they started at. What's the standard? And so scientists came together and they decided upon standard temperature and pressure. What's the baseline pressure? What's the baseline temperature that we should use in our experiments, said the scientists. And they decided upon the air pressure at sea level, which is 1 atmosphere, or 101.3 kilopascals, right? Different units, but the same value, right? Both of these things are equal to each other, and they are both equal to sea level. And standard temperature, they decided, would be the freezing point of water. Right, again, we have 0 Celsius or 273 Kelvin. Both are equal to each other. Right, so standard temperature and pressure, STP, is more than just an acronym. It is a set of values. If I tell you STP, or if you read in a problem or in a textbook STP, you know now that STP stands for an atmosphere, right, the sea level air pressure, and the freezing point of water. For our convenience, we have been given these values on table A of the reference table, the very first thing on the very first page of the reference table. Paired with that is converting from Kelvin to Celsius. Right? We're going to see Celsius temperatures, we're going to see Kelvin temperatures. It's important to remember that we can convert between them with a simple addition or subtraction of 273, depending on which way you're going. Funny enough, this formula is given to us on table T, and it is the very last thing on the very last page of the reference table. So, if I show you a problem that asks, what's the boiling point of water at standard pressure? What's the boiling point of water at sea level? You should be able to answer that. Here, our answer is choice 4. The boiling point of water at sea level is 100 degrees Celsius. Right? Table H lets us know that the boiling point changes at different pressures, but at sea level, at standard pressure, it's 100 degrees Celsius. When we make that conversion, Kelvin equals Celsius plus 273. Kelvin equals 100 plus 273. We get choice 4. So, as we move forward, as we talk about standard temperature, standard pressure, we know what those values are. If we say STP, we know that that stands for a temperature value and a pressure value. So let's start looking at relationships between our properties of gases. The first relationship we're going to look at is between pressure and volume. Scientists by the name of Boyle studied the pressure and volume of a gas, and he found that the two things are inversely related. So if I were to draw an inverse relationship, what would that look like? What's an inverse relationship? An inverse relationship, if I were to draw it, is a downward trend, either a straight line or a curve. Right? Starting high, ending low. When we look at the pressure and volume relationship, we see that it's a downward inverse curve. And we get a formula from this. We get that pressure and volume are inversely related, that P1 times V1, our initial, right, our before volume and pressure, are equal to our after volume and pressure, right? If I multiply pressure and volume, before and after, I should come to the same answer. Now, this makes sense if you think about it in terms of our gas particles, right? We defined these things in terms of gas particles. Pressure is how frequently they hit the walls of the container. Volume is how much space they take up. So if I shrink the volume, if I decrease the volume, if I make those particles take up less space, they will hit the walls of the container more often. If I look at it the other way, if I have a small container and I make it bigger, I let the gas expand, the gas will hit the walls of the container less frequently. right? This is an inverse relationship. As one goes up, the other goes down. So that means if I were to ask you a question, something like this, and give you this formula, you should be able to solve it out. Solving out this problem, I've got a pressure and a volume given to me in the same sentence. These are my before, right? My pressure and my volume before. The volume is changed, so I've got an after. What's my new pressure? When I come in here and I start plugging in, I get 1 atmosphere. Remember, this is multiplication. Times 7 liters equals P2 times 3 liters. Divide both sides by 3 liters. Liters cancel out to give me 2.3 atmospheres. Right, 7 divided by 3 is 2.3, and the only remaining unit I have is atmospheres. You know that it's not choice 1, because liters is a unit of volume, and we're looking for pressure. And if you added instead of multiplied, you got choice 2, right? It's not addition between them, it's multiplication between them. 1 times 7 equals P2 times 3 liters, not 1 plus 7 equals P2 plus 3 liters. What if I asked you a less mathematical question and a more conceptual one? If I double the pressure on a gas, what happens to the volume? Pressure and volume are inversely related. If one goes up, the other goes down. If one gets doubled, the other gets cut in half. So pressure and volume inversely related. When one goes up, the other goes down. Let's look at another pair. A scientist by the name of Charles studied volume and temperature and looked at the relationship between volume and temperature. And the thing he discovered is that these are directly related. We saw an inverse relationship before. What does a direct relationship look like? A direct relationship should be an upward trend, starting from the origin and moving upward in both axes. Right, that gives us a graph that looks like this. Right, as temperature increases, volume increases. As volume decreases, temperature decreases. And again, we get a formula that compares a before and an after. This time, instead of multiplying them, we are dividing. So it's V1 over T1 equals V2 over T2. But we still have our before and after. We look at our relationship, and it always remains this constant, both increase together or both decrease together. Now, does this make sense in terms of our definitions? Right? Volume is how much space they take up, temperature is how fast they're going. If I increase the temperature, if the particles move faster, the particles will spread out more. If I decrease the temperature and make the particles move slower, the particles will contract and come together a little bit. And so this makes sense logically when you think about our definitions. Now, we've got to point out that temperature is measured in Kelvin here, not Celsius. And that's actually really, really important. If we're talking about temperature and saying that temperature relates to the speed of the particles, to the kinetic energy of those particles, we need an absolute scale. Now, what's an absolute scale? An absolute scale is something that starts at 0 and goes higher. There's no such thing as negative mass, or negative volume, or negative pressure, or negative energy. Right? I can't hand you a bottle that holds negative 6 liters. Right? It doesn't make sense to have negative values for those things. And so those things are measured in absolute scales, something that starts at 0 and goes higher. Temperature, though, we've got a bunch of different scales. Celsius and Fahrenheit both go into the negatives, where Kelvin starts at 0 and goes higher. Kelvin is the only absolute temperature scale. It relates directly to how much motion there is. 0 Kelvin means no motion. 0 Celsius doesn't mean no motion. 0 Celsius means water freezes. Right? Celsius goes to negative 273 and then goes higher. Kelvin goes to 0 and then goes higher. And so if we're talking about doubling energy, doubling temperature, doubling how fast the particles are moving, Kelvin is actually the only one that shows doubling motion by doubling the number. If I go from 100 to 200 Celsius, I am not doubling the motion of the particles, right? I'm not doubling the speed of the particles. I'm just increasing by 100 Celsius. Because Celsius starts at negative 273, its true 0 is not 0 Celsius. And what this really boils down to is that anytime you are plugging in or using temperature in a gas law equation, you must be using Kelvin. If you're looking at volume over temperature, these temperatures had better be in Kelvin, otherwise you are getting the wrong answer and your math will be wrong. And this is leading to one of the bigger tricks that tries to get pulled on you when you're looking at Regents' gas law problems. If I give you a practice problem, you'll see Kelvin has to be plugged in. They gave you Kelvin in the problem, but your answers are all in degrees Celsius. So this is not just about solving. This is about solving and then converting your answer to Celsius. Give it a try. When we solve this problem out, we plug in our values, right? Temperature 60 Kelvin, right? That's going to go in T1. Volume 3 liters. Our volume gets changed to 7 liters and we're solving for T2. When I solve for T2, I get 140 Kelvin. Now, like I said, this is the biggest trick they can try to pull on you. Kelvin is not the same as Celsius, so our answer is not choice 3 here. We need to convert this value to a Celsius value, so we need to plug in to our formula here that we take off the back of the reference table, saying that 140 equals Celsius plus 273, Celsius equals negative 133, making choice 2 our correct answer. You need to be careful about units. If you're not keeping track of your units, you pick choice 3 and you get the answer wrong. This was Kelvin, so it will come out on the other side as Kelvin. Your answers are all in degrees Celsius, so you must convert before you get your answer. Now, what if I asked you a less mathematical question? If you double the volume of a gas, what happens to the temperature? Temperature and volume are directly related. When one goes up, the other goes up. So if I double the volume of a gas, I double its temperature. Our third pairing is the pairing of pressure and temperature, studied by a French scientist named Lussac. When he studied pressure and temperature, he found that those two things are directly related. similarly to how volume and temperature are related. We get a graph that goes directly up, and a formula that looks very similar to our before and after formula for volume and temperature. Right, we've got pressure over temperature equals pressure over temperature. Again, we need to keep in mind that we're using Kelvin here every time, otherwise you're going to get your answers wrong. And these also make sense if we think about them in terms of the definitions. Pressure is how frequently particles collide with the walls of the container, and temperature is how fast the particles are going. If the particles are moving quickly, they collide with the walls of the container more often. If the particles are moving slower, they collide with the walls of the container less often. And so we get the same formula that we had for volume and temperature, except now we substitute pressure in. And the same tricks and traps that we fall for with volume and temperature, right? Having it in Kelvin or given to us in Celsius and asked of us in Celsius at the answers, right? And all those conversion tricks that we are going to not fall for are going to happen here as well. But there's actually one more gas law, one that doesn't look at individual pairs and actually looks at the relationship between all three pieces at once. This is made by a guy named Avogadro. Avogadro said if I have two boxes of two different substances, right? Let's say there's ammonia in one and oxygen in the other. If these two boxes have the same pressure, the same temperature, and the same volume, they have the same number of particles in them. And this makes sense to us as well if we think about the definitions of our properties. Each one of these things, temperature, volume, and pressure, relate to how the gas particles are behaving. If the gas particles take up the same amount of space, move at the same speed, and hit the walls of the container with the exact same frequency, we can say that there's the same number of particles causing those effects. Right here, there, let's say 3 or 5 particles, and here also then 5 particles. However many ammonias are causing these effects, the same number of oxygen will cause those effects. Now, relating to that, Avogadro said that 1 mole of gas would take up 22.4 liters of space. And Avogadro is going to come back in another unit because of this idea of the mole. A mole is a word that means a number. The same way you go to Dunkin' Donuts and you ask for a dozen donuts, or you go to the grocery store and you pick up a dozen eggs. A dozen means 12. If I ask for a dozen of something, I will be given 12 of those things. A mole, just like a dozen, is a word that means a number, except it means a much bigger number, 6.02 times 10 to the 23rd power. When we talk about it in chemistry, we're talking about atoms, or molecules, or particles. things that are teeny tiny. And when we take something that is very large and combine it with something that is teeny tiny, they kind of cancel each other out and bring us a normal amount of something. All right, so when we talk about how much a mole of something weighs or how much space a mole of something takes up, we get actual measurable values. All right, a mole of carbon is 12 grams. That's something you can hold in your hand and measure on a scale. 22.4 liters is an amount that you can capture in bottles or balloons. And we're going to come back and we're going to really look at a mole in our later units. But for now, I've got one practice problem to wrap us up for the day. How many molecules are in 5.6 liters of gas? Right? How many moles are in 5.6 liters of gas? If we know that 1 mole is 22.4 liters, 5.6 liters is how many moles? When we look at a problem like this, we know that 1 mole is 22.4. So if we have 5.6 liters, we're making a proportion. When we solve this out, we're going to get a quarter of a mole. Right? 5.6 is a quarter of 24, and so it is a quarter of a mole of particles. And with that, I'm going to transition us over to our Zoom meeting for questions, comments, concerns, and attendance. And I will see you there.